Okay, so just going to run through three quick examples on de Moivre's theorem. The first thing to say just before I jump into the first one is de Moivre isn't completely kind of new and out of left field. If you look at these three properties of cis that we would have done in the last class, the property one was that cis A multiplied by cis B is equal to cis A plus B. So to add two cis's, or sorry, to multiply two cis's, you can just add their angles. So in this first example I'm doing here, evaluate cis 45 to the power of 12. What's cis 45 to the power of 12? It's cis 45 multiplied by cis 45 multiplied by cis 45 multiplied by cis 45. So you can just keep adding those 45s together. Okay. What's the same thing as adding 12 45s? It's 45 multiplied by 12. And that's what I'm going to get when I use and apply de Moivre. Okay, so it's not entirely new. It is just building on that property that you've used already, albeit there is a formal proof there for de Moivre you need to be able to reproduce. But as I said in the notes, I will do that after we've done induction because it uses induction in the proof. All right. De Moivre is on page 20 in the formula book. It's the same page as the minus b and the binomial theorem, which you'll use. The matrices there you don't need anymore. Just to say, I suppose, example 3 that I'm going to go on to, minus 4 plus 4i to the 6. De Moivre is a much quicker way of doing that than multiplying it out 6 times. I suppose you could use the binomial theorem to do this, but look, de Moivre will be a lot quicker to put that into polar and then use de Moivre. But just supposed to cover that off. But no, once it's in complex numbers, use de Moivre rather than the binomial. All right. So anyway, this first example here, evaluate cos 45 plus I sine 45 to the power of 12. Let's write out de Moivre's theorem. And as I said, this little bit here at the end, you don't need. All right, so it's just this bit here that you're interested in. So, or times cos theta plus I sine theta to the n is equal to or to the n on cos n times theta plus I sine n times theta. All right, so or times cis raised to some power, you can evaluate that by raising the modulus to that power, so I get the or to the power of n, and then multiplying the n by the angles. Okay, so whatever the angle is, you're going to multiply it by the power. So to do this one out, I don't have an or here, I don't have a modulus. You can write one if you want, but there's no need. All right, so I have got the cos of 45 plus I sine 45 to the power of 12 in this case. And I'll just work down the page here because I don't have a huge amount of space. That's equal to the cos of 12 times 45 plus I sine 12 times 45. Let's work out 12 times 45. It's 540. So this is equal to the cos of 540 plus I sine 540. That's it raised to the power of 12 in polar form. But as I said in the notes, whenever it says evaluate, it wants it back into rectangular form. Okay, it wants it in that a plus bi form. So if it says evaluate, that's what it wants. Sometimes it will be more explicit and say in the form a plus bi or in the form x plus yi. But just if it says evaluate, it wants it back into rectangular form. So don't leave it like this. All right, to get that back into rectangular form, you just evaluate this. All right, so I'm working in degrees, so calculator's in degrees mode. The cos of 540 is -1. I sine 540, so sine 540 then is 0. So plus I times 0. Anything times 0 is just 0. So the cos of 45 plus I sine 45 raised to the power of 12 is just equal to -1. All right. Second example I will do here is, again, it's already in polar form, but this time I've got a modulus. Okay, I've got 2 cis 60 raised to the power of 5. All right. If this is an exam question, I'd write the Moivre's theorem out. I'm kind of done a huge amount of space here, so I won't do it, and I've already done it there. You'll see I have less and less space to do these as I go across, like when you write a poster and your last few letters are really, really small. To do this one anyway. So what do? You raise the modulus to the power. So I'm going to get 2 to the power of 5. And then, like I did in the last example, multiply the 5 in. Okay, so 2 cis 60 raised to the power of 5 is going to be equal to 2 to the power of 5 on the cos of 60 times 5 plus this I sine 60 times 5. So that's equal to 2 to the power of 5 is 32 times 60 times 5 is 300. So just cos of 300 is a half plus I, and then that's going to be sine 300. So sine 300 is minus root 3 over 2. That's equal to 32 by a half is 16. 32 times this, I could work out in my head, but just to be sure, I will do it on the calculator. I get minus 16 root 3. So minus 16 root 3 I. So there's 2 cis 60 to the power of 5 back into rectangular form. So that's it. Evaluate it. All right. Last example I will do then. So evaluate -4 plus 4i to the power of 6. This one's in rectangular form. Okay, so to raise this to the power of 6, I'm going to need to change it into polar form first. Okay, you can do that by hand if you want to, out the Argand diagram, draw your right angle triangle, figure out the angle, figure out the modulus. I'm just going to do it on the calculator. All right, so -4 xy 4, second function 8, and I've got 5.65. Okay, so I'm gonna need to do something with that modulus. It's not in the kind of surd form I want, it's in decimal form. My angle is fine. Okay, so I'm gonna have something cis 135. Okay, so again, that modulus is stored here in the x above the RCL on the calculator. So just alpha x is equal to that. So if I square that, it's 32. So it's root 32 is my modulus. So it's 4 root 2. Okay, so this -4 plus 4i is the same thing as 4 root 2 on the cis of 135. And then, as in the question, that's all raised to the power of 6. All right. So to do that out, you're going to raise your modulus to the power of 6, and then it's going to be times the cos of 135 times 6 plus I sine 135 times 6. So let's try. I might spread it across 2 lines here. So that's equal to 4 root 2 all to the power of 6 times the cos of 135 times 6 plus I sine 135 times 6. Okay, so 4 root 2 to the power of 6 is 32,768. On the cos of 135 times 6. So, I mean, you can rewrite this out and evaluate it, or just plug it into the calculator as it is there. So cos 135 times 6 is 0. Plus I times the sine of 135 times 6 is 1. So 32,768 by 0 is 0. 32,768 by 1 is 32,768i. So 32,768i is our number evaluated in rectangular form. So just like in that first one, I just ended up with a real number, no imaginary part. Second one, I ended up with just an imaginary number, no real part. Second one, I ended up with a complex number with both a real and an imaginary part. I've done all of these using degrees. It's perfectly fine to do them using radians as well. Okay, you will get the same answer in the end.